Hello everyone, welcome to all of you in my YouTube channel. In this today's video, I'm going to discuss about one of the famous experiment of quantum mechanics that is called Davisson and Germer experiment. So, what is the purpose or what is the principal aim of this experiment is the main aim of this experiment is to demonstrate the wave nature of electrons, right? In general, electrons are considered as particles, right? But after the de Broglie hypothesis, as de Broglie gave a statement that every matter poses a wave or wave particle duality means particle should possess wave nature and wave nature should also possess the particle nature, right? After the hypothesis of de Broglie, this experiment was conducted, and in this and through this experiment, Davisson and Germer successfully verified that electrons, they are the particles and they show the diffraction phenomena. So from that, as the electron shows the diffraction phenomena, it means electron shows the wave nature. Electrons already are particles, no doubt about that. And from this experiment, they confirmed that electrons possess the diffraction phenomena. So this shows that electrons or the matter shows the wave nature. They verified the de Broglie hypothesis, we can say. The overall schematic diagram for this experiment is as shown in the figure, right? So from the figure, it is very clear. You can see a filament which is written as F here. The work of filament is to eject the electrons. When this filament is heated by low tension battery, LT means low tension battery. When you heat the filament by this low tension battery, the electrons are emitted or the electrons are ejected from the filament, and these ejected filaments are accelerated towards A, because this the D1 and the D2 are connected to the positive potential of the high tension battery. ST means high tension battery. They are connected to the high potential battery. These negatively charged electrons which are emitted by the filaments are attracted towards the Ds, or we can say they are accelerated with the high velocity towards A by the D's, D1 and the D2, or we can say that the beam of electron is collimated, means a fine beam of electron is accelerated towards the A, and this setup sometimes is also called the electron gun, because it is in the shape of gun, because a fine beam of electron is ejected from the point A. The highly collimated beam of electron, we can see that you can see that the dotted ray is actually the beam of electron. This beam of electron is actually the highly accelerated beam of electrons then strike on the nickel target, and when they strike on the nickel target, the electrons beam are scattered. The scattered beam is collected by this collector, you can see that, and again this collector is connected to the galvanometer, right? So the intensity of this scattered beam is directly proportional to the deflection of the deflection in the galvanometer. So high deflection in the galvanometer represents that the intensity of the scattered beam is high. So here is handle to just to move this nickel target, and this collector can also be rotated in a graduated circular scale. So this is the very basic setup. In the below descriptions, all the things which I already told are explained there. The experimental arrangement for Davisson-Germer experiment is shown in the figure. It consists of electron gun. As I already told you that this represents this setup is sometimes called electron gun, because from the point A, a fine beam of electrons are ejected. So that is why this setup is also called the electron gun, right? Do not confuse with that term. The electrons are produced by heating the filament by low tension battery. I have already told about that. These electrons are accelerated by the potential applied with the high tension battery. the electron beam is collimated with the with the slits D1 and D2 in the gun. The high velocity electron strike the nickel target. I already told that. The scattered electrons, the scattered uh, electrons are collected by the collector, which can be moved along the graduated circular scale so that it is able to receive the reflected electrons, because all the scattered electrons it will collect. It can able to receive the scattered beam from the angle 20 to the 90 degree. The collector is connected to the sensitive galvanometer, as you already seen that, whose deflection is proportional to the intensity of the scattered beam. As much as the intensity of the scattered beam, more is the, the deflection we can observed from the galvanometer. So the beam of electrons are made to fall normally on a crystal from the electron gun. The galvanometer current is recorded in various position by rotating collector. By rotating the collector, we can collect the different galvanometer current. The angle between incident beam and scattered beam, which is represented by theta at various accelerating voltage, is noted. The observations are rotated for observed for different accelerating voltage, and the number of curves are drawn from the figure below. So now what happens, we just for the different accelerating potential, different graphs we obtain. For 40 volt, there is not so much spur or bump is seen. So as we start to increase the accelerating potential, the this bump or spur, sometimes is called, also called, its length is increasing, and and we seen that at the potential of 54 volt, and at an angle of 50 degree, this spur or this bump is maximum in amplitude. On further increasing the accelerating voltage, again the spur is decreases, right? The length of spur is decreases. So what is the cause about this? This is because of the high the high bump or spur is due to the constructive interference occurred from the different planes of the crystal. So it is these are the results, and the graph remains fairly smooth till the accelerating voltage become 40 volt. Up to the 40 volt, the graph is quite simple, quite fair. As the accelerating potential increased, the length of spur is also increases. You can see that from increasing the potential from the 40 volt to the 48 volt, 54 volt, but the length of the spur is continuously increasing, right? As the accelerating potential increase, the length of spur bump increases. It reaches maximum value at 54 volt at an angle of 50 degree. With on further increasing the accelerating voltage, the length of bump decreases and finally disappears above 68 volt. At the 68 volt, again, then it will be disappear on further increasing the accelerating potential. The occurrence of this high bump, at 50 degree with the electrons accelerated through 54 volt can be explained due to the constructive interference of the electron waves scattered in this direction from the regularly spaced places. So basic cause behind this is that there is the interference of the scattered beam which are scattered from the different planes of the nickel crystal, right? So now we can use the de Broglie hypothesis. From the de Broglie hypothesis, lambda equal to h upon p. So h divided by p means 2 MeV. So if we put the value of mass 9.1 10 to the power minus 31, charge of electron 1.6 10 to the power minus 19, and yes, we also put the value of s 6.62 10 to the power minus 34, and on calculation we will get 12.38 upon root over v in terms of angstrom. So now, as we have seen the pronounced bomb high interference at the potential of 54 volt, so the lambda will be 1.66 angstrom. So and then according to the experiment, this is the theoretical part from theory. this voltage, this wavelength we have gained is from the theory. According to the experiment, we have diffracted beam at 50 degree for the potential difference of 54 volt for nickel target of 111. This is the Miller indices. 111 target. This is actually the name of the space, specifying the plane. We can say that reflective plane with the crystal spacing d is equal to 2.15 angstrom. Now applying the equation of plane reflecting grating d sin theta equal to n lambda, and we just put the value of n is equal to 1, and then we will get the lambda is equal to 1.65 angstrom. What we have seen from theory, we are getting the value of 1.66. From experiment, we have getting the value of 1.65 angstrom. So what does this shows? Thus, the experimental value is in close agreement with the theoretical value. So this shows that the beam of electron behaves like X-rays, suffers diffraction at reflecting surfaces, and behaves like and has the wave-like characteristics. So from this experiment, we can conclude that the electron beam poses the diffraction. It means that electron beam poses the wave nature. So this is the major principal aim of this experiment. Thank you very much.